if I look at something like this, we have a couple approaches to this. I could take a specific logarithm of each side, but most of the time it's easier just to go right to the natural log. So if I take the natural log of each side, that allows me to bring the exponent out front using my properties of logarithms. And now I can divide each side by the natural log of 7. So I get x minus 5 equals this logarithm of 100 divided by the logarithm of 7. And now I could add the 5 to each side. And after I do that, it essentially just becomes a job for my calculator. And I will show you real quickly how to plug this in to make sure you don't make a mistake. But really, it's like doing our change of base formula. So we do the natural log of 100 with parentheses divided by the natural log of 7. And me personally, I'll take order of operations into my own hands and I'll let the calculator do it. So I'll hit the enter button there and then add the 5 to it, okay, without rounding off until the very end here. So I get something like 7.366, and then another 6 if I'm rounding to 4 decimal places because that 5 rounds up, okay? If I look at the next one, let me just scoot my calculator off to the side. I'm going to need it momentarily. The first thing I'm going to do with this one is also take the natural log of each side, but let me write it over here just a little bit. Give myself some space. Especially here when I have two different bases, I just want to go right to the natural log of each side. So I take the natural log. That allows me to bring the exponents out front. And again, I don't want to round this off until the very end. So I'm going to distribute this natural log of 5 to each of these. That gives me an x natural log of 5 plus 2 natural log of 5 equals 2x natural log of 8. Now I have to gather my x values. I want to get them on the same side, so I'm going to subtract this logarithm from each side. And again, I can't plug all this in yet. I want to wait till the very end. So I'm just going to leave it as a 2x natural log of 8 minus x natural log of 5. And now that I have my x's gathered, what I'm going to do is I'm going to factor out that x value. So over here I had the 2 natural log of 5. Over here I can factor out the x, which leaves me with a 2 natural log of 8 minus the natural log of 5. And now to solve for x, I'm just going to divide by that entire thing in parentheses, which is the 2 natural log of 8 minus the natural log of 5. I do that same thing on each side. So over here, they're going to cancel out, of course. So I'm going to find out that x equals. Well, now this is a job for my calculator. If I want to plug this in the way it's written, here's what I have to do. Always surround the numerator with parentheses. So it's parentheses 2 natural log of 5. And you have to close the parentheses around the logarithm. Then you also have to close the parentheses around the entire numerator. Divided by, again, entire denominator should be in parentheses 2 natural log of 8. 8 gets surrounded in parentheses to keep it in the logarithm, minus the natural log of 5, which is also in parentheses to keep it around the logarithm. And now I have to close the parentheses for my entire denominator, which gives me this. So that's a 1.2626. Okay? If you wanted to simplify this a little bit first, keep in mind that this guy right here, if we think of this big giant fraction, we can simplify it a little bit. That 2 that's in front of the natural log of 5 can go up as an exponent, so it becomes the natural log of 25. In the denominator, the 2 goes up to the 8, so it becomes the natural log of 64 minus the natural log of 5. And then I can combine those using division, so it becomes the natural log of 64 over 5, which I can plug this into my calculator. It's like doing my change of base formula, and we'll see the same answer come out. The natural log of 25 divided by the natural log of 64 over 5. And I get the exact same thing. Okay? If I take a look at the next one, it says an investment of $1,000 is earning 8% APR compounded quarterly, and we want to find the number of years needed for the investment to double. All right? So this is my standard model for growth. which is y equals a times 1 plus r raised to the t. Remember, the key here is to make sure all of our units match. So right now, I know the initial amount is 1,000. The rate is 8% APR, but it's compounded quarterly. Keep in mind, APR means annual percentage rate. So if I'm getting 8% per year, how much is that per quarter? I have to divide that by 4. Okay? So I do the 0.08 divided by 4, which is a 0.02. So that's my quarterly rate, which means my time then that I'm looking for is going to come out in quarters. So just be aware of that. And I want to know when my investment's going to double. In other words, I want to know when I'm going to have 2,000 in here instead of 1,000. And now I'm going to solve this for t. I divide each side by the 1,000. I'm isolating the exponential part of the function. So I find out that 2 equals the 1.02 raised to the t. And now I take the natural log of each side just like I did in the previous examples. That allows me to bring the t out front. So I have the natural log of 2 equals t natural log of 1.01. Let me rewrite that up here. And now from here, I just have to divide by that logarithm, just like I did in the last example, except this one's not quite as complicated as that. So I'm going to divide each side by this natural log of the 1.02. And again, it's important to note that since this thing was per quarter in terms of my percentage, once I plug this in, my time is going to come out in quarters. So when I do the natural log of 2 divided by the natural log of 1.02, it gives me 35.00. So 35 exactly almost. And but that's 35 quarters, which that's a unit of time that doesn't make much sense to us. So I'm going to divide that by 4 to find out the number of years. And the number of years is 8.75. And that's a unit we're familiar with. So that's the unit I'm going to keep it in. Okay? If I look at the next one, it says the population of bacteria at time t in hours is given by the population equals 500 e to the 0.12 t. And so this is my continuous model for growth, and it's already set up for me here. And I want to know how many bacteria are there when t equals 0. Remember, time equaling 0 is the initial amount. Well, the initial amount is right here. It's the 500. Okay? I shouldn't have to do too much in order to identify that. Time equaling 0 is the initial amount. That's 500, and that's it. You can plug the 0 in for t, and you should come up with the same value when you plug this in. The next thing asks me, what is the growth rate constant of this particular strand of bacteria? So the growth rate constant is the k value, which is located right here. So my growth rate constant is 0.12, and I should slap some units on there. That's per hour. And I know it's per hour because time is given in hours. So my growth rate has to be per hour. And then if I want to know what is the population after 3 days, well, I just have to plug that time value in. So I do 500 e to the 0.11 t. And the trick here with this time is that I have to plug it in hours. So if this is written in days, hours would be 72 for this one. Okay? I got to make sure my units math, so the population after 72 hours. Now this is just a job for my calculator, so I plug in the 500 e to the 0.12 times 72. And it looks like it gives me 2826. Oh, I'm missing a 6 in there. Let me try again. And I probably wouldn't count 0.9 of a bacteria, so I'm going to round this off to the nearest bacteria, which is going to be 6.5. So 2,826,665 bacteria. Okay. Taking a look at the next one. The next one asks me to find out when will the population reach, and this comma is obviously in the wrong place here. It should be here. When will the population reach 1 million? So really, all I'm doing is setting up the same thing. I've got the 500 e to the 0.1112 t this time. T is the thing I'm looking for, so that's my variable. And I want to know when this is going to equal 1 million. So now I just have to simplify this. I divide each side by 500. I'm isolating the exponential part of the function. So I do the 1 million divided by the 500. So I get 2,000 equals e to the 0.12t. Now I can take the natural log of each side. The natural log and e cancel out, so I'm just left with the natural log of 2,000 equals 0.12t. I divide each side by the 0.12. So I find out that t equals, well, it's just a job for my calculator. Okay, so I plug it in. Looks like 63.34, and again, that is in hours. It's important to include the units here so I know exactly what we're talking about. All right. The next one, I want to do the same thing. I'm asking when will the population double. So I've got 500 e to the 0.12t. I'm solving for time, and I want to know when this thing equals 1,000. So I divide each side by the 500. So I find out that 2 equals e to the 0.12t. I take the natural log of each side. Natural log and e cancel once again. Natural log of 2 equals 0.12t. Divide by the 0.12. So I find out that t equals 5.78. Again, that's in hours.